Okay, so today we'll do Sarna's theorem and in the simplest possible setting. So you get a feel for large deviation. Kind of big picture issues involved. So these are, I'm kind of following tempo and Zutini, large division applications, ancient chapters. Maybe I think I'm going to get Sushant to, after I've done 3-4 lectures, ask him to give a more advanced lecture. The first time that he's reading. Do it outside the lecture time. Okay, so the idea is as follows. So suppose you're given a distribution mu. Okay, and we'll keep things simple. We assume that the support of mu is. So we assume that the support is sigma, which is finite. So A1, A2, A2. So finite. And the so under mu random variables are coming taking values over there. So mu A1, mu A2, those are probabilities. Okay. So now you ask yourself, what's the chance that I see an empirical distribution by of n samples? So what does ln by mean? Ln small y is going to be collection of ln small y. Let's make it a vector. ID samples. This is ln y p1. Now with ln I is simply counting y. I'm just counting the direction of the fraction. So I look at this empirical distribution and what's the probability that this is equal to mu? So that's a big thing. It should be mu. What's the probability it looks like mu? Now you can imagine this illustration. Like there's a probability measure mu. You generate samples. What's the probability? You cover the empirical probability measure. What's the probability it's in the neighborhood of some distribution? That's, I mean, more generally, we have to look at like this. But it's cleaner here. This we'll argue looks like e to power. So we'll make this precise in a moment. But the first dominant term is e to power n h mu mu.
That is scale level.
That is scale level. So now you know what scale level is, right? But you see that it actually comes up very naturally in our division.
This was actually the information relation.
In the?
Information.
Yeah. So you have to ask yourself that is information theory in some sense kind of linked to large division? And at the end, it's you want to keep the codes far away so that the probability of incorrect interpretation, decoding is small. It boils down to these large division probabilities. So you have to look at this kind of quantity. And in some sense, this justifies it. So where this is like now, h nu mu is summation mu ai and then log of mu ai upon mu ai. This is a crucial point you keep in mind. It's a measure of distance, so to speak. Then it's not distance in the proper sense. But nonetheless, you have a distribution mu. Further mu is larger this value is, more rare this event is. That's all captured from here. It's defined by this quantity. And what you need to keep in mind, just as a rule of thumb, is the underlying distribution is the denominator here. Because it's always confusing which one is nu, which one is mu. So the underlying distribution from which the data is coming from shows up only the denominator. Nu is what data looks like. That shows up in the numerator here and here. Because that's worth keeping in mind. Now, H nu mu had better be non-negative, right, for this to make sense. So why is it non-negative? Can you see? Jensen, right? You can just come back here and this is just expected value under nu of log of nu y upon mu y, right? Okay, and then I can write as minus e nu log of mu y upon mu y. Now I take the log is a concave function. I'll take the expectation inside, so I get a lower bound, right? This is equal to 1, this is equal to 0. Right? Yeah, so this is greater than equal to 0. Okay, so this is very crisp. So this is what we want to show. But let's be a little more exact now. So what we show is as follows. We show that e to the power minus, no. We show that the probability that under measure mu ln of vector y looks like nu that's going to be less than or equal to e to the power minus n h nu mu. It's going to be greater than or equal to e to the power minus n h nu mu. And then you have n plus 1 or minus 0. We are precisely. This is a polynomial term, so it doesn't show up as a show. But you can see that the things will get more complicated when your state space becomes infinite. Then all the simplicity will be lost. What's that? Huh?
Like proving this entirely equal to the
Information is really easy. In this context or
Method of
method? Okay, so you can help me and go through the steps. Since I'm only prepared for those steps, we go to them regardless. Right. Just done this or is it just a while ago? Oh, so it's good, so it's revision.
Yeah.
Okay, good. And then the point of this is essentially the large negation statements are made much more abstractly, and the flavor is as follows. That you look at minus infimum, yeah, nu lying in some set gamma naught h mu is less than or equal to limit n goes to infinity 1 by n log of probability that n and y lies in set gamma, and that's then soup. That's what this minus gamma closure gamma. So gamma itself here is m1 sigma is equal to p1 through pd p sigma. Zero summation. So this is the probability simplex in this sigma dimension. Absolutely, this cardinality. So your gamma is a subset of it's a correction probability. And this is the open set, and by open I mean in the relative interior of the sigma. That's the closure. Again, the induced closure. Okay, so this is the flavor of large division result when we get abstractness. And when we prove something like this, we say, okay, the sequence L and Y. So I'll discuss this more accurately and more generally and more abstractly later in another lecture. But we'll say the sequence satisfies large division principle. Large division principle with rate function. H. So that's what this kind of means. This is a rate function, right? Yeah. Yeah. This is when the underlying guys are coming from wave. So then this empirical distribution finds that's why it's LDP is a rate function. So we'll come to more abstractions later. Right now, let's just get the intuition. Okay, so now we have to prove that inequality of yours. Okay, so let's see how do you help me in that. We'll start by looking at what shall we start with? Yeah. Keep my notes like this. Yeah. So let's take so let me collect all possible empirical distribution. So I guess all types is possible, right? Corresponding to what I want to say is that all we define this that is notation for this way. And is entitled. So all and y bar for y bar, and let me call this a small y. Sigma. Okay. So this is collecting all possible empirical distributions. Now I ask myself, what's the probability under mu that y1 through yn is equal to this particular y? That's that ln y is equal to nu belonging to ln. A particular outcome, what's the probability that I see this? So this is just going to be mu ai I equal to 1 to sigma, and this should be, I guess, number of times I see this, right? So that's going to be n times uai, right? Let's see what's the chance of seeing a particular outcome. Why? Okay, that's going to be exactly this. With each AI is happening and new AI types. Okay. What does this look like? I can rewrite this as
E power 1000 log in mu.
Right? Okay, and this I can re-express or minus n equal to sigma mu ai log of mu ai by mu ai. Right. Right. Yeah, it's going to be plus. Yeah, so it's mu ai log of mu ai. So it should be correct. I had here. Now it's just for log. Yeah, I know, that's fine. Yeah, that's it, it should be minus, yeah. Yeah. Because I've added log mu as and that's in that source, exactly. And the point is, you define entropy of distribution nu to be minus mu that. No. Take it. So then this looks like basically e power minus n h mu plus h. Right. So each sequence has seeing a particular sequence has a small probability, there's an extra h mu here. So now we do, when we say an empirical distribution looks like mu, we'll count all such sequences. Right, so P mu, I guess, ln y bar looks like mu. I'm going to count DC. So all the outcomes where the empirical distribution is new. And that into e to the power minus n h mu plus h. And HU is also non-negative, right? That you know again mathematically. Okay, now let's define so mu is basically y and sigma n ln y, I guess. Right? Okay. So I mean, as you probably already have seen, so the game becomes okay. How many elements should we have here? And that's the interesting part. So, how many outcomes give the same empirical distribution nu? That turns out to be exponentially then. And interestingly, the further nu is from uniform distribution, larger this value. Right? That's kind of you know you've seen it before, but otherwise it's a little non-intuitive. That's why that should be the case, right? Okay, so then I mean all we really need to complete the story is we need to show that you know this guy here. Then we are back to where we want to be in this. Now the big picture, as I'm saying, is that this is essentially exponentially. That's this by. In fact, h nu is the cap is minus summation nu ai log of new AI. So I can, I guess, divide by 1 by sigma. It's same multiplying by it. So I subtracted it, now I have to add it. So plus log of so what this is saying is that this h nu looks like log of sigma, which is what you achieve when your new AI is uniformly distributed, plus relative entropy with respect to uniform distributions. No, this is, oh, that's right, but it's minus. Oh, that destroys my story.
The size of TN is largest when the.
That's right, yeah. No, sorry, yeah. So just, it is what I was said before. Yeah, I was wondering why that was the case. I missed the sign. Thanks. Yeah, so this is exactly, this is minus h nu, and then I guess let's call it uniform distribution plus log sigma. So yeah, so maximum entropy is when you have uniform distribution. And now the world is what it should be. This is surprise us. Saying that I will be going this minus sign here. Yeah, so it becomes less. Essentially, this is we're counting, right? So it should be that it's maximum for uniform. It should be lesser for non-uniform, and the more non-uniform you are, the lesser it should be. That makes total sense. Yeah. So this is captured by it. Okay, good. Okay, good. So now we just need to prove that guy over there. So help me prove this. This is on for what?
Maybe over the temperature 22.
You know what's the mess with it? Okay. Okay, how do you prove the upper bound here? What's that? Or you want to go for that? P of mu ln or all new in ln, right? This is going to be equal to 1. Then
I'm saying that for that probability is going to be equal to 1 for a particular
is probability
this is going to equal to 1 for
less than equal to 1. That's all.
I'm not saying the summation.
Okay. Now what do you do?
Now TNV into that term is equal to 1. So that time that term goes to the right side. It will be to the power n. Yeah. But there should be a minus before h n given.
Okay, so your point is that this, of course, is given by that expression.
Yeah.
Okay, so that will give you some kind of upper bound.
But there should be minus before the h new given new.
And we take this to be under new.
That's right. Yeah.
And
So you take this under new, and then you know that okay,
distance becomes 0.
h new is equal to. Okay. So then you get that okay, this probability is less than equal to 1, hence e to the power minus n h nu into t n nu is less than equal to 1. Is equal to 1. Okay. So that's a nice thing that we can kind of play around with changes of measures. We can use our own measure. And this is not a bad measure because you expect this probability to be high, right? It's not that you've got a very huge boundary. This makes sense. Okay, the other way around, the other direction. One that you use.
Quality of the problem factorial by k factorial greater than equals.
What's that?
In the assignment, there's this inequality factorial by k factorial
Yeah.
greater than equals to k power n minus k.
Why is it? You use that basically.
And so that under mu this term is maximized when mu equals to mu.
Chalo, so let me just try to write that exactly similar to argument on. I may have a different proof technique for what you're requiring. You don't use Sterling's approximation, do you?
Yeah,
No.
yeah.
Then I think it will be the same. The point I guess is this that what we do is we look again at P nu ln y equal to nu. But we also compare P nu and then that's probably what you're referring to, right? Nu prime,
Yes, and if you mu, the probability mu will always.
and we'll say this again next course. Yeah. That's also a very nice result, right? You expect it to be true, but to actually have it shown is nice. This is for all nu prime. Right. So once you show this, then you have the okay summation P nu ln y equal to nu overall nu in L. So it's collecting the number of possible empirical distributions. This should be equal to 1, right? Something wrong here. Nu prime. Right. And now you say, okay, this is going to be this quantity here is greater than equal to. If that is true. Right. And then we get that so you get that okay. So, I guess we plug in the value here. So this will be Tn nu is greater than equal to e to the power n h nu again. And then we get and now okay, you say size of this guy, it's just sigma elements. Each element can take value 0 by n, 1 by n, 2 by n, at most n plus 1 values. So this overall size can at most be n plus 1 h to power. Cardinality sigma. This is okay, so we are basically done. We just need to show this part. That you also kind of know. And essentially, you observe that here just multi-normal probabilities, right? So you can just expand this and then simplify. Okay, so this is going to be equal to, then we have yes. So n factorial gets cancelled, so we have that sigma, then we have n mu prime ai factorial on n mu ai factorial. Then you have from here, I guess you're going to have mu ai to the power n mu ai 1 mu prime. Right. You see here.
So we know here. That distribution is still new.
Yeah,
You.
Oh yeah, that's right. So this should be new. But yeah, that's what it takes. First time. Okay. You know the remaining calculation, is that right?
I've done this.
So you know the whole calculation. Okay. So what will we do? We'll just kind of, I guess,
As inequality that n factorial by k factorial is greater than or equals to k power n minus 3.
yeah, that's essentially what's going to do this for us. And then whatever is remaining is going to be equal to 1. And so then the whole thing gets dominated by. Okay, so I can leave it then, right? Safely. Okay.
Is there any other way of doing that without using that?
You can use Sterling approximation.
Yeah, but that would give an asymptotic, like, that would give an like I can't say that that inequality goes for smaller.
True. This is all exact right now. That will be asymptotic. And I guess the question is, are there bounds in Sterling approximation? Probably not. Could I use bounds in your fairly tight bounds? Right now I don't. I mean, I guess one could probably try some kind of change of measure arguments. But I've not thought about this. So maybe one expresses this under measure mu prime, and then you take the likelihood ratio, and somehow try to show that with the likelihood ratio. But it's so to your question, I don't know the answer. But typically one tries these change of measure arguments, and then you can go far. That's what I would try. You don't like this argument because it's too much kind of this competition.
I mean, yeah, like I'm just trying to avoid the
Yeah.
Yeah.
Right. But yeah, at the end, of course, you just want to show that.
You can also make it because it's based on integral of ln. And ln is complex. So by choosing the correct side, you can say it's the approximate integral is strictly less than the exact.
So I guess it's a good store for me, but essentially you want to show me that this is less than this quantity, right? That's a very intuitive thing to say. What's your proposal?
So he's saying that you don't want to use Sterling because it's only
Yeah.
but you can get it exactly. But because it's integral of based on integral of ln, right? Which is increasing. So by choosing only the left side and only the right side, you can. So similar to how you can say that Harman numbers are strictly normative for the.
So what number is it?
It's a harmonic number. Okay. So similar to that.
I guess in some sense one wants a more kind of an intuitive proof for this, right? Because you expect the motional mass is here, everywhere else it should be less. So I mean, I would just kind of go to this probability, maybe express this under the change of measure mu prime, like the likelihood ratio, and somehow argue that. But how do you argue from that? It's not apples to apples. You want to make it apples to apples, right? The other thing can be that I come to this, you express this in terms of then but once you come to likelihood ratio, you kind of but that's likelihood ratio per argument. That may be easier. It's not all, there's no combinatorial term. It's just that I'm going to look at this term and re-express this as an expectation under mu of the event that ln y prime is equal to mu and then all the other terms. And somehow argue that all the other terms are less than equal to 1. That could be the way to try. All you need to show is that the remaining terms are less than 1. We go to 1, then you get a problem. That's all you really need. So if the attempt is something as follows, that P nu ln is equal to expected value of nu indicator L is equal to nu prime. Hard to say. I guess what you want to show is this. Indicator ln y equal to nu minus indicator ln y prime. I want to show that this is. So I don't know, can one couple them in such a way that whenever this is 1, and sometimes this is 0, this is 1, and then you get the inequality. It's hard to say like one can make that work. Maybe for Bernoulli at least one can, and then one can do some inductive problem. Yeah. One can play around with these things. I've never looked at these things. But the idea is intuitive, so you want to come up with a nicer proof. That I really agree. Okay, so where are we? So we are now at P mu ln y equal to nu is less than equal to e to the power minus n h nu. That's what we have. Right? So from this kind of nice looking inequality, we want to make it really ugly. Kind of get into generality that one typically expresses largely in results. And the point of that, it's good to see that because it also tells you that that really has this kind of stuff as underlying intuition. That you know, so each mu, seeing mu essentially looks like this. That's what really matters. So now we go and ask ourselves, what's the probability that the mu ln y belongs to some set count? Okay, that's what we're going to do. And what is that? That's going to be just summation probability mu ln y is equal to nu, and nu belongs to gamma intersection ln, right? It has to be an empirical distribution. So that's the whole thing. You know, when we sum these things up, because we are only interested in the dominant term, which is exponential, what really matters is the one which dominates. All the others are tiny relative to that. So we also exploit that. Let's do that now. Okay, so what do we do here? So you can write this as, I guess, because we can upper bound this, right? So let's upper bound that first is summation mu in gamma intersection ln e power minus n h nu, right? That's the second further upper bound by cardinality of ln e to the power minus n infimum mu in gamma intersection. Right. That's the whole thing, that everything I'm adding on is not really contributing to the exponent, it's not changing the exponent, so I can do these things. So now I can further upper bound this by n plus 1. It's just a polynomial. Polynomial is one doesn't care about in this word, small terms here. And I can further bound this by 1 minus n infimum gamma. Right, I can get rid of ln. If I expand the set here, I'm taking infimum over a larger set, I get a smaller value, negatively not good. Right. This now the upper bound that I want to prove follows. So 1 by n log of probability mu empirical distribution lies in gamma. Lim sup of this as n goes to infinity is less than or equal to minus infimum mu in gamma h. Wait, I get this. And I can even close this and nothing, it only helps. Right. The thing is, I don't need to close it here, but there are applications where only things work out when you do closure. So you'll do some homework, so you get to see this thing. Okay, so upper bound came quite easily. Lower bound requires a little bit more work. So let's see. So now we want to look at P mu and then y in gamma. But that's really telling you, it's intuitively that's what's telling you that all these things boil down to summing over all possible outcomes. And essentially the dominant outcome is what matters. And it could be that you have more than one dominant outcome, but you can have polynomially many, that's still okay. You can still you and those things. That's what I've been doing some sense all about. You're optimizing over this set to find which among this set which is most likely. So that's why the point that unlikely events happen in the most likely manner. That's what's being factored in. So this is again, I'm going to write as summation mu in gamma intersection with ln. Mu, right? Now I have a lower bound there. So n plus 1 the part minus sigma. And then I have here, you'll allow me this, right? If I put why don't we do that? I mean, I can just look at the max for lower bound, right? So the max is one term, isn't it? They're polynomially many, so I'm not again being very loose. So I just put here e to the power minus infimum gamma intersection ln, which right? That's a lower bound.
We max
You see, by my yeah, it's one element, right?
Yeah.
That's the whole point. The element exists on both sides. On the upper side, it's this plus all the small things. In the lower side, please, this guy is still there. So this tells us that okay, lim inf n goes to infinity 1 by n log of greater than equal to, then we have I guess minus lim sup as n goes to infinity Theorem of gamma intersection ln H. I guess new license. New. ठीक है. Okay, and now I know that. So let me take one new in the interior of. Okay. So because it's in the interior, there's a neighborhood around it which also belongs to gamma and M1 sigma, right? And eventually all the ln's are going to lie in it. Because I know that, okay, d of any mu with ln, and by d I mean the total variation distance. This is, I know, what do I know? I know d of variation distance. Mu prime is just equal to summation mu ai minus mu prime ai. I put one to sigma 1 upon 2. That's total variation distance. So now, in ln, I can always find a point which is 1 by n close to, for any mu, I can always find a point in this collection which is 1 by n close to it at most in each dimension. In each dimension, right? Okay. So that means this thing I can upper bound by in each dimension 1 by n, there are only these many dimensions. Right? So these guys are going to be at least 1 by n. So I get sigma upon n by 1 by n. Okay. So that means that if I give you any mu, I can find a point ln which is within 1 by n order. So I can find a sequence of points in ln and then goes to infinity, which is converging to mu. So I can find mu in ln so that mu n is converging to mu. Now, some things I have not discussed very much. So you have to be more cautious. Okay, I give you this mu to begin with. Mu had some support. It could be that mu is not full support, and the mu we are talking about is more than mu. So that is mu is giving mass somewhere where mu is 0. But then h nu mu becomes infinity. So that doesn't really matter so much. Those things. That's why I'm without loss of generality. I'm just considering all the news having the same support or less support than mu. It's not becoming okay. So now I've got this. Let me see this thing. Okay, and the claim is now because I have an infimum there, right? So let me look at this. Let soup minus infimum h mu mu. Mu is in gamma intersection ln. H gamma mu minus mu. This is infimum. So I can dominate from negative of that, I can dominate from below by h of mu and mu. And this is just equal to h. So I get this lower bound for my probability. So basically what have I achieved? For new lying in interior. I needed new to lie in interior. Then I could construct a sequence. And then my whole argument worked out. So now I have this load bound for every new lying in. So it also is true for the theorem. And that's all I claim. Okay, so everything works for this. So this is all I want to discuss today. I thought we'll stop early. But the plan of action, I guess, is we'll do Cramer's theorem and then Untitled theorem. So I guess Cramer's theorem is, as we were discussing earlier, that's more of the form is probably with Sn by n lying in some set G. Right, and you want to say log of this limit when the limit exists. This looks like minus from some function x minus a. That's going to be the large deviation that we prove for Sn by n. But the intuition is still going to be, as we discussed last time. Let me talk briefly about that. Intuition is probably the Sn by n looks like some x that is going to be minus n lambda star x. So that's the intuition that we're going to take and prove those kinds of results. But let's just understand what this lambda star x. So this you've just seen in the last lecture, right? You've not really seen it before. Lecture we did 2 lectures ago. So what's going on here? So this lambda star x is very interesting. You can think of this as infimum because this, Sn by n is when the underlying distributions are coming under. They're coming so under distribution mu is underlying distribution. So it's infimum over h mu, where under nu. So so Sn is equal to summation of xi I equal to n xi distributed as mu. Okay. So E mu of x is equal to small. So now it kind of makes sense, right? That how does the sum look like x? It's taking a large deviation. Each large deviation, so the mean is equal to x. It looks like, so this is mu such that e to the power minus n h mu. All of these can potentially cause the mean of Sn by n look like x, mean of x. But amongst them, which one is the most dominant? That's the one with the smallest value of h mu. So I get the infimum here, and that's why this works. So it kind of fits in with Sarno's theorem. But otherwise, you can get it through Chernoff. This is what we were saying last time. So lambda star x is also equal to supremum theta x minus lambda theta, where lambda theta is equal to log of e to the power theta x. It's a log of variable. And this kind of points to the relationship, the duality that exists between the Kullback-Leibler distance and log Golding functions. Have you seen that somewhere? Or? So they're very nice. We'll see them as we go along. Maybe in the next lecture I point to. But this duality is quite abstract. One version of this is in the Donsker-Bertrand representation of Kullback-Leibler distance. I don't know if I remember it correctly. But me bring that up next time when it comes to the topic of text.
So the statement of Sanderson was that equal to 1/8 plus 1 power.
Yeah. It was that with the logs and all that.
Which one?
With the logarithms and the lim suits and the limits.
Oh.
Yeah, that was the Sanderson. Yeah. And the main thing is that that result goes more generally on abstract space.
But external product.
Empirical, but so even more abstract, I guess you mean even outside of IID or say,
Okay.
even Markov chains, yeah, even that. But right now, I'm just saying that IID where xi, empirical distributions, first of all, xi themselves could have general distributions. They don't have to have finite support. But they also need not just be in real lines. So xi could be elements in a Polish space, complete and separate spaces. So even in that setting, you get a sound. So that's the whole point of it, that to get that generality, the logarithmic version still holds. All the other things cannot be. So this we'll discuss next time, but you've seen this kind of stuff before. This is you probably know that this is a convex function, like log one function. You know that or?
Then dual.
What's that?
Is some dual, ancient dual.
Yeah. So you did Fenchel dual recently or?
No, you were saying.
I was saying it, yeah. So this is a Fenchel dual of this function, and then this is has a similar representation with respect to lambda star rays. So they are
Gamma equals to the gamma prime of gamma prime.
yeah. Typically, right? The mild assumptions, yeah. So we'll see all of that, and then, but this will, the way to get this kind of result is to kind of turn over. So next time what we'll do is first we'll use Sarnaf's theorem in the finite setting and get Cavier's theorem from there, just using all the Sarnaf's theorem machinery that we have. And second, we'll prove these kinds of results, Sn by n lying in A. Both when Sns are general distributed in the real line, but also in Euclidean space. And then we'll ask ourselves, okay, how far can we go beyond IID random variables to prove these kind of things? And that's the Cartesian theorem. So that's my plan for this initial keyboard lecture.
What is the reference textbook for this?
The reference textbook is large deviations, theory and application, Dembo and Zutini. Okay. And what we are doing here is and what I want to do if I get a chance is that they also have a small section on concentration inequalities. If I get a chance, I'll do it, but otherwise you can read on your own. And that could also be something for you to consider presenting if you want to read up on those things. Concentration inequalities and the nice topic. So we did chapter 2 today, some part of it. No, we did chapter 3, sorry. No, we did chapter 2, sorry, we did chapter 2 today. We'll carry on doing chapter 2, I guess. Yeah, I mean, all we are doing is basically chapter 2 in this book. That's what we're doing. In the end of chapter 2, in 2.4, you see concentration inequalities. So that you should have a look at. Right, but later chapters are more interesting. So there's, general principle, there's sample path large deviations. So you have whole paths and they take a large deviation. Then you have LDP for abstract empirical measures. This is what I meant by Sarnaf's theorem in general setting. Okay. We'll start with this. Chat here. Camera focus has become bad. Okay, next time we'll remember that. Sorry, just saw that.
No, it was improved, like later it improved.
Oh, it became better?
Yeah.
All right. Okay, we'll see you guys later. Bye.